So one of the things we wanted to learn in our discussion of the fifth model of quantum numbers is how do they know the numbers of electrons that are on each of the different energy levels? Well, through quantum numbers, they were able to realize that the first level only had one sublevel made up of one orbital. 1 squared is one orbital. Each orbital holds 2 electrons, so the first level only holds 2 electrons. And that's where we had that with Bohr's model. Bohr's model, we only put 2 electrons on there. On the second level, we put 8. The second level had a total of 4 orbitals. 2 squared is 4. Each orbital holds 2. That gives you 8. So you can use that same idea to understand that it's the number of orbitals on a sublevel that actually determines how many electrons that level holds. For instance, the fifth level. We learned a while back that the fifth level holds a maximum of 15 electrons, or 50 electrons. Where does that come from? Well, the fifth level has 25 orbitals maximum on it. 5 squared is 25. Each orbital holds 2 electrons. Regardless of whether it's an SPDF orbital, it holds 2. Now, on the fifth level, they don't actually ever need to put 50 electrons because we've got the SPDF. The G is actually not needed. The G would have a second number of 4. So how many orbitals would make up the G if they needed it? If you remember, you take the second number times 2 plus 1, and that gives you the number of orbitals. So 4 times 2 is 8, plus 1 is 9. The G would hold 18. Remember, the fourth level held a total of 32 electrons. There are 16 orbitals. 4 squared 16 times 2 is 32. So how do we go from 32 to 50? It's because the next sublevel held 18. 4 squared is, I was about to say that wrong, that fourth sublevel, or that sublevel when the second number is 4. 2 times 4 is 8, plus 1 is 9. It holds 18 electrons. So if the fourth level held 32, the fifth level, we add this additional sublevel in there that holds 18. 32 plus 18 is 50. But that one's not used. Why is it that 8 seems to be the magic number? It's because when you can fill the S and the P, the sublevel, those sublevels, the S and P sublevel, those are the sublevels that contribute to chemical stability in the atom. The S has 1 orbital, spherically shaped orbital, holding 2. The P has 3 hamburger bun or dumbbell shaped orbitals, each holding 2 for 6. 6 total. 6 plus 2 is 8. You now understand where the octet rule comes from. Why is there a duet rule? Well, the first energy level, as we saw, the first energy level only has one sublevel, the S, and the S is made up of 1 orbital, which holds 2. So the first energy level is filled with 2 electrons. That moves us on to the third and fourth numbers. The third quantum number is the one that's called the magnetic quantum number, and it's abbreviated M sub L because the third quantum number's value depends on the second quantum number. The second quantum number's abbreviation was L. This is the one that assigns you to a particular orbital. And each of the orbitals, if we notice, had a different orientation. So for instance, there's a P that goes along the x-axis, and one that goes along the z, one that goes along the y. So sometimes they designate it px, py, pz, or p minus 1, p0, p1. So how do they get that third number? That third number is allowed to be minus the second number to positive the second number. That's why it's abbreviated M sub L. So if your second number is 0, the second number is L, the third number has to be a 0. If the second number is a 1, the third number is allowed to be minus the second number to positive the second number, as it says right up here. So it's minus 1, 0, minus 1, 0, and 1. That's 3 numbers, so there's 3 orbitals. Each orbital holds 2 for 6. So when that second number is a 1, you know there's 6 total electrons that'll fit in the 3 orbitals that make up the p sublevel. When the second number is a 2, you were in the d sublevel. How many orbitals made up the d? There was 5. 5 orbitals made up the d. What are the numbers we give to those orbitals? Minus the second number to positive the second number. Minus 1, minus 2, minus 1, 0, 1, 2. That's 5 numbers. There's 5 orbitals. Each orbital holds 2. That's 10 electrons in the d. Minus 3, minus 2, minus 1, 0, 1, 2, 3. Where did they come from? The second number is a 3. The third number is minus the second number to positive the second number. So when an electron has a first, second, and third number, that third number is putting them in an actual orbital or house. As we mentioned, the energy of an electron or an orbital's energy is determined only by the first and second number. The third number does not affect energy. The third number is just assigning an orbital based on an arbitrary or an imaginary orientation of that orbital within the atom, within that sublevel. Again, the third number is minus L to positive L. First number puts you on an energy level. The second number puts you in a sublevel, which is made up of one or more orbitals. The third number puts you in an actual orbital. What does the fourth number do? Remember, each orbital holds 2 electrons. The fourth number is called the spin quantum number. It's abbreviated m sub s for spin. Electrons actually spin as they move. 2 electrons in the same orbital must have opposite spins. This is according to the Pauli exclusion principle. So if an electron in an orbital is spinning one way, it actually creates a magnetic field. A spinning electron creates a magnetic field, which will cause an electron trying to spin the same way to flip and have the opposite spin. Spins can be clockwise or counterclockwise. Which is clockwise and counterclockwise is also an arbitrary assignment. Plus half is given to the one designated as clockwise. Well, the other one is spinning the other way, so it's counterclockwise. It's given a plus half and minus half. If you've noticed that we have 2 electrons in an orbital, negative repels. It's the fact that the electrons are spinning and creating little magnetic fields that help overcome that repelling force of 2 negative particles. Those are our 4 quantum numbers. But when we look at our 4 quantum numbers, we want to remember that the quantum numbers are not trying to tell you where an electron is. It's just giving you a probability. Heisenberg's uncertainty principle says it's impossible to determine the momentum, an exact location or direction electron is moving at the same time. Quantum numbers are just probabilities. You can never be certain where an electron is or where it is moving. We mentioned that electrons try to occupy the ground state. The ground state is the lowest energy possible in the atom. Everything wants lowest energy in the universe. So electrons seek to have the lowest energy. The Aufbau order of filling. Aufbau is a German word meaning building up principle. So electrons automatically will try to go to the lowest energy level first. That's the first level. And it'll try to fill the lowest energy level and then fill the lowest energy sublevels on a given level that has more than one sublevel. So if we are on the 4th level, as we were talking about in here, here's the 4th level, or 4th street. The electrons will fill 1st, 2nd, 3rd street first, and then they'll begin filling 4th street. I should say that for the most part, that's what they do. But when they start filling the 4th street, they will go to the S first. Then they'll begin filling the P sublevel second. They go to the lowest sublevels on that level first. We'll get more into that later, but the Aufbau just says that electrons will go for the lowest energy levels, sublevels combination first. the N plus L. The energy, as we mentioned, you add the first number, the N, to the second number, L. If two electrons on different energy levels have the same energy, in other words, if the N and L's from the different levels are tie, the tiebreaker goes to the lowest level. And we'll get more to that in our next discussion when we begin looking at electron configurations, orbital notations, and those sorts of things. We'll talk a lot more about how to know the order of filling. For now, you just need to know that they go to the lowest energy level, which is the lowest energy first, and you get the energy by adding the N plus L. Once again, electrons in the same orbital, electrons on the same level, in the same sublevel, in the same orbital must have different spins. That's called the Pauli exclusion principle. And basically what that's saying is no two electrons can have the same set of quantum numbers. A given electron is excluded from having the same exact quantum number set as another electron. If they have the same first number, if two electrons have the same first number, they're on the same level. If they have the same second number and first number, they're in the same sublevel. If they have the first, second, and third number the same, they're actually in the same orbital. But if they're in the same orbital, they have to have opposite spins. So the fourth number would be different, which is really what the Pauli exclusion principle is saying. What kind of problems did we have with this fifth and supposedly final model? Well, they had not yet quite discovered the neutron yet. That wasn't a big problem. The neutron was discovered shortly thereafter in 1932 by Chadwick. The fifth model doesn't address weird things about the nucleus, such as the fact that the protons and neutrons and electrons are actually made up of other particles called quarks. They had not yet been discovered yet. But for the most part, for chemistry, the fifth model is the one we need to understand a lot more about electrons. In our next video, we'll take a look at how to put together quantum numbers. In our final video, we'll look at some practice problems with quantum numbers. If you have any questions on any of these, do not hesitate to ask.